Good afternoon, and thank you for joining us for our Beyond Hyperconverged webinar, introducing our new product, Cloudistics Ignite. We are very excited to present the vision, technology, and benefits of our super converged enterprise cloud platform and show you the simplicity of our SAS Portal. Our CEO, Naj, and CTO, Srinidhi, will present the solution and the technology. That will be followed by our CXO, Partha, who will present the actual demo. Because we're introducing our new technology, we really value your feedback and participation during this webinar. Therefore, I'll be posting a couple poll questions as we go along that I will reveal the answers to throughout the webinar. As you guys may have heard, we have a couple really fun prizes for participation today. The two people who tweet the most about this webinar, as well as those who participate in our poll questions, will actually have a chance to win a $50 Amazon gift card. Please tweet at Cloudistics with the hashtag BeyondHCI, which is the hashtag for this webinar. We will announce the winners at the end of the webinar as well. For a chance to win the iPad Air 2, please complete the survey that will launch at the end of the webinar. It will just pop up in your browser, so please don't close your browser screen after the webinar is complete. We will announce the winner of the iPad Air 2 at the beginning of next week, so definitely keep your eyes peeled for a Cloudistics email. Now I'll hand it over to our CEO, Naj, who will walk you through the vision of Cloudistics Ignite.
Thanks, Tessa. Hello, my name is Naj Hussain, CEO of Cloudistics. Every once in a while, a product is introduced to the market that revolutionizes the way businesses think about IT. We are very excited to introduce one to you today, and we call it Cloudistics Ignite. The most advanced IT infrastructures today are called public clouds. They are easy to use with minimal infrastructure management. They are pay-as-you-go. They scale elastically. Who wouldn't want that? They make businesses a lot more agile. Public clouds actually shift IT's focus from managing complex infrastructures to building and managing services and applications. This is much more value add to the business. However, many enterprises have applications that require control of their apps and data by keeping all the data behind the firewall. Predictable costs. Think about it. How are you to know how many IOPS or bandwidth your SQL app's going to use today? It's literally impossible. They also want predictable performance. Because of this, many businesses are moving quickly to adopt a new infrastructure strategy that is much closer to the public cloud model to improve operational efficiency and reduce costs. We set out to leapfrog all these challenges with an infrastructure platform that delivers the best of the public cloud with the control of an on-premises infrastructure. A platform that is way more focused on delivering services and applications. We even have native support for Docker containers, so you can run both virtual applications and containerized ones on the same platform. We also have a platform that is as easy to use as the public cloud and can be managed from anywhere. A platform that delivers decoupled scaling of resources. A platform that delivers on-premises control of your apps and data. A platform that delivers predictable performance with high-speed virtual networking and virtual flash storage. And a platform that offers predictable costs. This is what Ignite is. It's an interplay of software and hardware. We modeled the usability and architecture after the public cloud by converging everything: network, storage, compute, virtualization, and SaaS management all into a single enterprise cloud platform with decoupled scaling of resources. We call this super converged. It's simple to use and eliminates storage, network, and virtualization management silos. It's 5x faster than VMware in both storage and networking. And it's 2x less expensive to scale than public clouds and traditional HCI solutions. You have been promised a future of software-defined everything for a long time now. Cloudistics delivers on that promise. Now back to you, Tessa.
Thanks, Naj. I'm going to hand it over to our CTO, Srinidhi, who's going to introduce Ignite's technology.
Infrastructure at that time, and that infrastructure that has continued to progress through, is sort of a siloed management infrastructure. So if you look at a traditional architecture in a data center, you've got networks that are separate, typically Cisco or Juniper or Brocade, with their own management stack for their platform, iOS or Junos. Similarly, storage is its own element, with its own management complexity. You had EMC over there, or NetApp, or HP or Dell. Compute usually involved just management of hardware. There were a couple of solutions there. And virtualization was its own stack, and that was vCenter, and VMware being the predominant player. This architecture is a fairly good architecture. It has scaled well. It has stood the test of time. Several large data centers are based on this. The issue here has been complexity. And over the years, as features have accreted, this complexity has grown and grown to the point where it requires a team of specialists to manage it. And this is what 3 years ago led to the movement towards hyperconverged infrastructures itself. And hyperconverged infrastructures, the basic idea is you build a single building block. It's a combination of compute and storage. So it's local attached storage with compute on board. Storage is usually the biggest pain point for enterprise applications. That is usually the cost that seems to slow things down. And by combining storage and compute, the idea was you would have a single plane of management for both compute and storage, and you'd probably see performance improvements there. Network was still a separate element, and virtualization continues to largely remain VMware in that space. So while compute and storage are tied together, there is one issue with this architecture. It does simplify management, but it comes at the cost of flexibility. Your upgrades are now coupled because compute and storage are within one platform. The ratio between compute and storage is fixed. And so now later, if you want to add more storage, you can't just add more storage, you also have to add more compute, and vice versa. If you just want more compute and your storage situation is fine in terms of capacity, you still end up having to add more storage. It is that coupled scaling that causes issues. This is what led us to superconverged and our architecture. And there were two sort of drivers that distinguish superconverged architectures from hyperconverged architectures. The first is we have virtualized everything. So in superconverged, the network is virtualized, compute is virtualized, and storage is virtualized. All three elements are virtualized. So the 10-year promise that we've had of software-defined data centers, Ignite is the first product that delivers on that promise. It is virtualized everything. You can set up networks through software, you can set up your storage through software, and you can set up compute and applications all through software, everything through the same interface. The best part of it is managed from a SAS portal. So there is no longer a need to set up vCenter on premises and then worry about redundancy of vCenter on premises. And being in a SAS portal, one of the biggest advantages is it already does multi-site, multi-geo management. Since the SAS portal can see not just hardware at one physical site, if you have multiple data centers or remote offices, all of your hardware, all the applications in your entire infrastructure, independent of where they are, can be managed from a single portal. The second part that is the distinguishing characteristics of superconverged is decoupled scaling, true decoupled scaling. So in decoupled scaling, if you wish to add more storage, you just add more storage. There is no compute coming along for the ride. Similarly, if you wish to add more compute, you just add more compute. There is no storage inside the compute. So this is the basis of Ignite, and this is the core elements of it. And now I'll get into what the solution looks like and what the technologies are behind all of those. We believe this is the only way that people are going to be consuming hardware in the future. Fully integrated hardware, software, superconverged architectures. So from a hardware perspective, what does a superconverged system look like? As I mentioned earlier, superconverged is on-premises hardware managed from a SAS portal. So what does on-prem hardware look like? There are three elements to Ignite. There is a network block, a storage block, and a compute block. And each of them can be scaled independently. The network block is a 48 by 10 gig router, and it also has 6 40 gig ports for connectivity into data center backplanes. This is a true software-defined networking router. It's a true SDN router, and our network virtualization is implemented directly in hardware within the router itself. The second element is the storage block. The storage block has two storage controllers, and these are on the top left and top right. And the bottom left and bottom right are effectively disk slides. Our storage block is all flash. All our storage solutions are all flash. In fact, there are no spinning disks in the entire system. Even our boot disks are flash. But if you look at a storage block, the disks in there, a base unit might start at 12 terabytes of usable capacity for all flash. And this is actual usable capacity. You can give it non-compressible, non-dedupable data, you'll still get that capacity. But when you start at 12 tera, we follow a scale up and scale out design philosophy. You can literally expand from 12 tera to 112 tera within the same 2U just by adding drives. And you can do this while the system is online. So while it is still serving production workloads, you can add drives and increase the capacity. And so within 2U, it goes from, and this is the scale up part, it goes from 12 tera to 112 tera. Once you cross 112 tera, you can simply get a second storage block, start that at 12 tera and climb it to 112 tera. Our storage subsystem automatically does federation. So when you add a second storage block, it federates with the first block and creates a larger common pool of blocks across all your hypervisors. You can scale this system to petabytes. And by adding a second storage block, you're also adding more IOPS, you're also adding more network capacity, and the performance scales linearly. Each of these storage blocks connects into the network block, and that is how hypervisors access the storage. It connects into the network block at 40 gigs per second. So each controller is 40 gigs, it's dual redundant, so there's 80 gigs going in basically. The third element is the compute block. The compute block basically is sledded. There are 8 sleds basically, and each sled is a completely independent hypervisor. Each sled contains 2 Xeon sockets and associated memory. We are based on the latest Intel Broadwell family of CPUs, so the V4s basically. Each of those sockets can take a 10-core, 12-core, or 14-core part, and 3 different memory configurations, 128, 256, or 512 gig of RAM per sled. Interesting thing with this is you can scale in units of 1. So a base unit might come with 2 sleds populated, 6 sleds are empty, and you can keep adding sleds one by one. And each sled can be a different configuration. Some can be 10-core, some can be 12-core. You could also have different memory configurations. There's no requirement for this to be uniform. So this is the basic hardware platform. So what does the software look like? As we said, we are a complete stack. We do both hardware and software management, as all the way from hardware management up to applications running on the platform across multiple data centers. And that is the value of the platform. Fully integrated, single vendor. If there is any issues, we are the ones you call. From a software perspective, we provide a complete hypervisor and management stack on top of it. Our hypervisor is based on Zen. Zen is the core hypervisor in lots of large facilities. Our core hypervisor is based on KVM. And KVM is the core hypervisor in a lot of different facilities, including Google, Facebook, Apple in many cases, where iTunes runs this as their backend platform. Over the years, KVM has matured into a full enterprise hypervisor platform with pretty much any major capability that you can find within, say, a VMware ESX hypervisor. You have it in KVM as well. Major things that we provide include ability to live migrate, full and para virtualization, complete hardware acceleration on Intel or AMD chipsets that use VTX. And we also provide some interesting capabilities like CPU and memory hot plug capabilities. So what this lets you do is, let's say you're running a SQL server that's got 4 cores and 64 gigs of RAM in a SQL Server VM, and the VM is running tight on resources. That is, it's being hit harder than 4 CPUs and 64 gig of RAM can handle. Within a running VM, you can add CPUs. You can say, give me 2 more CPUs into that VM and another 64 gig of RAM. And the running VM itself suddenly sees 2 CPUs pop up, and that's the hot plug part of it. And the additional memory pop up, and it can use it immediately. Normally, in previous generation infrastructures, you would have had to shut down that VM, add the additional resources, and restart the VM. This can be done online in our platform. So what are the core pieces of technology that are there in a Cloudistics Ignite platform? The first that is unique to us is the way we do virtual networking. So back in 2012, VMware bought a company called Nicira, and that led eventually to their NSX product line. So we took a look at NSX and the promise of what virtual networking had. So prior to that, people have virtualized compute, that virtualized storage. Networking was an element that was still tied to the physical world. The promise of virtual networking was that you could take a bunch of VMs and create a network entirely in software, and that network is decoupled from the physical network. Why would you want to do this? When you deploy multi-tier applications, you likely want to segment each tier of your application separately. And this is a technique called microsegmentation. Gives you better security, better control over the network infrastructure, and better utilization of exactly the resources that you need in order to get those applications to talk to each other. And if you can do this completely in software, this is something that you can set up and tear down on demand many times a day. Doing that on a physical network is hard. Typically, a physical network is set up for a variety of applications running on it, and effectively, in many cases, it becomes sort of lowest common denominator design. The network has to be general purpose enough to satisfy any application, not just the particular applications that you're trying to run on there. So virtual networking, by abstracting yourself out of the physical network, you also get the benefit that any configuration error is purely in software and doesn't take out network connectivity. If you have a misconfiguration in the physical network, a lot of unrelated applications are simply going to come right down. So virtual networking gave the promise of that simplicity. The issue that we had with NSX was not just the complexity of setting it up, but the overhead that NSX imposed because of the core technology it uses. So NSX is based on an encapsulating technology. So when a virtual machine sends out a packet onto the network, what NSX does is it takes that packet, puts it inside a larger packet. And that larger packet has its own IP header, its own UDP header, and its own MAX frame. The problem with that operation is it's very expensive. The operation of encapsulating and decapsulating at the other end, basically. It works fine at 1 gig line rates, but at about 10 gig line rates, it only operates roughly at about 4 gigs. Encapsulation in software is expensive. And then when you go to 40 gig line rates, those numbers continue to hold at 4 gig. So you're paying very high overheads. So effectively, it's become a devil and deep sea choice over here. If you want the simplicity of virtual networking, you're going to lose performance. If you want performance, go down to physical networks, in which case all the microsegmentation stuff becomes a real pain. This is this choice that we wanted to break. We wanted to deploy virtual networks everywhere. So back in 2013, we invented a technology for doing network virtualization that's patented, that operates entirely in layer 3. It does not do encapsulation. In fact, we operate by simply changing elements in the IP header directly. And we do that in literally a nanosecond. We operate at line rate on 10 gig networks, 40 gig networks, 56 gig networks, and shortly we will be doing it on 100 gig as well. In our network router, as an example, the hardware acceleration that is built in over there, we do network virtualization at 1.544 terabits per second because the ASIC can accelerate this directly. The second thing about Cloudistics Aeon and layer 3 based virtual networking is it significantly simplifies management of virtual networks as well. So if you go to NSX or any of the VXLAN based networks, when you have two virtual networks, you also have to have virtual routers and virtual switches, all of which are managed entities. And basically, you also have to have a virtual network admin at some point. That entire layer of complexity is gone in layer 3 based virtual networking. Your physical network that has already been set up continues to do double duty as a virtual router as well. So that entire layer of management complexity is gone. By getting this performance that Aeon provides, we are able to use it to connect not just applications to each other, but also applications to storage. So effectively, you can use virtual networking everywhere without any performance impact. The other thing that we did with it is all the microservices that you need to set up and manage virtual networks are built in. So normally when you set up a network, you need things like a DHCP server, maybe network address translators, NAT, firewalls, load balancers. They're all built into the solution. And security in here is built in. Our firewalling here is built in directly at the network layer itself. And it is distributed completely. Wherever a firewall profile is associated with the virtual network, and if a VM starts in the network, in that particular virtual network, it will run that particular firewall profile under it. So if you've got a virtual network for your application tier that happens to be JBoss, that firewall profile will simply allow only those ports needed for your JBoss-based application to work. It doesn't matter where the VM starts. The VM that belongs to the virtual network can start on any hypervisor. Each hypervisor understands what VMs are running within it, what networks they belong to, and correctly instantiates the right set of firewall profiles underneath to ensure that multi-virtual network, multi-application systems can all be hosted seamlessly on any hypervisor on the platform, wherever capacity is available. The second element where we have really unusual technology and that we spend quite a bit of effort in increasing performance and simplifying is in how we did storage virtualization. So if you look at a VMware infrastructure or pretty much any of the prior generation infrastructures, the basic idea there was you take a bunch of LUNs basically from SAN arrays, put VMFS on top of it, and then you have a VMware cluster, which is a series of hypervisors, up to 32 hypervisors in there. And that is basically your shared storage or your shared data store. In that shared data store, you create VMDK files, and these VMDK files become the disks basically of your application VMs. There are a couple of issues we found with this approach. First is the complexity of setting up and managing this construct called a VMware cluster of up to 32 nodes. And the complexity comes from the fact that VMFS is a distributed file system. And distributed file systems are hard. We have done this in the past ourselves. They're hard because they're complex pieces of code, they have reliability issues, and they don't scale well. So 32 nodes is the scalability limit of a VMware cluster, but not many people even run it at 32. They typically run it at smaller numbers because heartbeating and quorum management become an issue at that scale. The second problem is reliability. So let's take a 32 node VMware cluster that's in production. If you pull the plug on 4 or 5 hypervisors in there, what is the expectation that that data store is going to continue to remain connected on the remaining surviving hypervisors? Almost none. You either end up with data corruption, or if you're lucky, the data store gets knocked out without any corruption, but basically you lost connectivity. The second problem that you face with distributed file system-based systems is, and this happens even with NFS or shared storage-based systems, is the number of layers of translation that you end up with in going to a file representation of a disk, the VMDK. So whether the VMDK is on a hyperconverged vendor exporting their storage over NFS or CIFS, or whether it is coming through VMFS, the same number of translations are happening. So to see why this is a problem, consider a simple example. Take a SQL server. So when a SQL server within a VM writes to the database, first NTFS, which is the file system within the guest, will translate that write to the database file into a bunch of metadata operations, and from there to a set of blocks on the disk that it has to write to complete that operation. But the disk is not real. The disk is virtual. It's a VMDK file. So VMFS or NFS below comes in at the next level. It then has to do one more layer of translation to figure out, okay, which blocks are these really referring to? In the case of VMFS, there may even be locking across the VMware cluster to do the write operation, for instance, if it were a thin provision VMDK. Eventually, out of that layer of translation comes out a set of blocks on the SAN volume or the underlying disk of an NFS filer. And that is where the write finally happens. Multiple layers of translation. What we did is quite different with how we virtualize storage. So in our world, storage is a bunch of blocks. It is just a pool of blocks. So if you took one of our base units, say a 12 terabyte storage block, it is essentially 12 terabytes of block capacity. You can add disks and take it from 12 tera to 28 tera, or 56 tera, or 84 tera, or 112 tera, but it's a bunch of blocks. Now, if in the same example, if an application, in this case SQL, when it asks for a disk for its data volume, the original disk that it was going to write to, say it's a 4 tera disk, when it asks for the disk, that to allocate that disk, what the flash pool does is directly carve a chunk of blocks and allocates it to that VM. There is no translation, there is no file system in between. So now when SQL is writing to that disk, NTFS does a translation to figure out which blocks on the disk to write. Once it writes, that disk is not virtual. Adds a disk all the way through. By removing those layers of translation, we run 5 times faster. And that's a big improvement in there. Those of you that are familiar with VMware back in the day, this looks a lot like a raw device mapping in physical mode. And that is largely what it behaves like internally. The difference lies in the following. VMFS as a file system and even the NFS-based, filer-based systems, they offer several features that are interesting that file systems can offer. Things like thin provisioning, things like cloning, things like snapshotting, these are things that we implemented, and this is where our IP is. We implemented all of these directly at the block layer itself. And that is why this is not raw device mapping in physical mode. In raw device mapping in physical mode, you lost all the cool features that you got out of VMware. No more vMotion, no more snapshots, which basically made the solution kind of unusable. It is those features, enabling them at the block layer, that gives us our capability. It gives us the performance without losing any of the features. In fact, in that same example before, the SQL server, folks, and this happens with Exchange also, folks usually set up a big volume for their Exchange database or their SQL database because they expect to grow to that size. Because our disks are automatically thin provisioned, you don't have to grow to that size. If you set up a 4 tera disk, and if you're actually only using 200 gigs, that's exactly what is being used underneath. And now you can oversubscribe your storage. 2 years down the road, when you really need the 4 tera worth of capacity, and your checks on oversubscription are starting to get cashed, you can simply add drives to the system and expand. So you get to truly scale as you grow, instead of paying for all of this capacity upfront. The other thing that is interesting about the way we do flash pools is single instancing. So most systems that get deployed on storage, most applications that get deployed, people tend to create golden masters because they want to set up their applications nice and clean, things like SQL, things like Exchange. And then from the golden master, they create multiple instances based upon their needs. Our storage virtualization technology automatically detects when disks are copies of each other and lays out a single copy of the disk. It deduplicates at the level of the disk itself. And this is single instance storage. This gives you significant capacity savings. So even a usual, a base model that's a 12 terabyte storage array behaves much more like a 40 or a 50 terabyte array because that is the usable capacity that you end up getting out of it. So these are the two core technologies within the system. So what do we do for high availability, redundancy, and storage data protection? So first, our storage controller design is based much more along the lines of the flash storage vendors, like EMC VMAX all flash arrays, which is the highest end line, or a pure storage array. And our performance numbers are similar to those folks as well. We do not, for instance, behave like HCI vendors with local DAS storage. And there are significant advantages to the way that the flash vendors do have when they deploy large arrays. First, the disks that we use underneath. These are not just enterprise drives, but there are other unusual drives. Erasure coding is built into these drives to ensure that drives themselves do not fail and do not corrupt data. Corruptions can be automatically recovered within the drive itself. And it is this erasure coding that is unique to the higher end enterprise SSDs. The same flash drives that we use are also used by EMC in their highest end array. And there's a reason we pick these drives, because of their reliability. The second thing we do is on top of the reliability of the drive itself and its own erasure coding, we do RAID 5 groups of across 8 drives. Our system, fully populated, has 32 drives. Every 8 drives forms its own RAID 5 group, and then we do a RAID 50 span on the top of that. So when we say, for instance, that a fully populated array is fully populated single storage block is 112 terabytes of capacity. In reality, it is 128 tera raw, 112 tera usable. The system itself has dual redundant power controllers. It also has dual redundant storage controllers. So if one fails, the other automatically takes over. Site-to-site disaster recovery and replication is coming very shortly. We're talking about the next 7 weeks. And this will let you move applications as well as data from one site to another, not just for disaster recovery purposes, but you can also use it for doing workload migration. Retention policies and full backup capabilities are built into that as well. And the nice thing with our design is that everything is managed from a SAS portal. So if a site goes down, the SAS portal still sees the hardware in all your other sites. It's as easy as clicking on your secondary site, clicking on the VM that has failed, and say, start this over here. We're also doing backup to S3, Amazon S3, where you supply your own Amazon credentials, and you can back up applications and take them to S3. And next year, based upon those S3 backups, we'll also give you the ability to stand up instances and use this mechanism for doing workload migration from on-premises software directly to Amazon, and be able to manage both of them from a single interface. I'll turn it over for the next poll question.
Thank you, Srinivas. So let's look at the results of the last poll question. So it seems that we got a mix here of different businesses, so that's always exciting to see a variety. We will ask the last poll question before I hand it over to Naj to present the cost savings. So we're just interested in what storage challenges you are currently facing with your company. End of the life, need more capacity, those types of things. Also, if you guys are tweeting for that $50 gift card, please make sure to hashtag Beyond HCI just to keep the momentum going. Okay, great. So now I'll hand it back to Nash.
Thanks, Tessa. So the platform was designed so you can plug and play into existing infrastructures with minimal disruption. So literally, you give us power, you give us one network cable from our router to yours, and you're up and running. So the idea is that you don't have to disrupt your current operations, and you can then start to move applications that you want to our platform. So
So you can decide which ones you want to use and how and what types. You can also import applications directly from VMDKs or VHDs, so from Microsoft or VMware environments, making that very, very simple to do. So you can start to pull in apps as you find necessary. We also support things like Docker, which is fun. That's coming up soon, where you can natively support Docker containers, which is very powerful, alongside of virtual applications as well. So you can run those concurrently. So on the cost savings, so we have some huge cost savings here between superconverged versus hyperconverged. And the major difference is the way we scale. Since we don't couple storage and compute together, we can scale them independently. The cost savings just for 112 VMs is 2.1x over typical hyperconverged solutions. And all the way on a fully populated 5U platform, it's 3.6x difference in cost savings. And that's an architectural difference that we have a big advantage on. When you look at the same model for cost at a public cloud, AWS, it's equally as dramatic. So 112 VMs inside of Amazon were 1.9x more efficient in cost, and when you get to 448, it's 3.6x more efficient in cost. So it's very dramatic price differences.
Great. So now Naj is going to take you through the SAS Portal.
Imagine this experience as you consider a proof of concept. You roll in a 5U enterprise cloud. You plug it in, you connect one port from our switch to your switch, and you power it on. All you need is a set of IPs from your network administrator. Typically, registering an infrastructure takes several specialists and days and months to deploy. With Ignite, you can easily log into our portal, register your infrastructure, and deploy apps in really under 12 minutes. It's really amazing, and I'm going to show you that now. For this demo, we have already created an account on our SAS management portal. All accounts are fully secured with multi-factor authentication. The hardware for the demo includes our base 5U system. It includes a 48 by 10 gig E switch, 2 nodes, each with 32 cores and 128 gig of RAM, and 14T usable all-flash storage. And as we discussed earlier in the presentation, you can scale all these components independent of each other. From the portal, now let's enter your service tag. A service tag uniquely identifies the switch and associates that switch with your account. Let's enter the unique IP range that you got from your network administrator. This is all you need to configure our router. Okay, now we'll save the configuration. The router is now configured with the unique range we just entered. What you see here is the physical representation of the enterprise cloud. At the top, you see the network switch. Below that, you see the node, the host assets. Below that, you see the flash pool. Now, if you highlight the ports on the switch themselves, you can see exactly where they're connected to. That one right there is connected to the WAN. That one's connected to the management network, and so on. You can see the two blue ones there connect to the hosts themselves, and that's automatically detected in the system. Register the two hosts and the flash pool and put them to use. Okay, we will start with the hosts. Let's give it a host name, a password for physical access if you ever need it. We will assign a host to a migration zone. Since we are in Reston, Virginia, let's call this migration zone Reston. And just think of a migration zone as a physical fence around a group of hosts. It's an important aspect when defining multi-geo configurations. Now let's register the second host as well. We'll go through the same steps. Okay, the two hosts are now registered and ready for use. We will now register the flash pool. Our flash pool capacity is true usable capacity. It's not deduped capacity. Our flash pool is all block, and storage virtualization eliminates the overhead of a distributed file system, making it 5x faster than first-generation hyperconverged systems. So that was it. We're all done with storage. No more SANs, no more LUNs, no more multipathing. It's all taken care of and highly optimized right out of the box. That's it. The infrastructure is set up and ready to go. Pretty simple. With other solutions such as VMware, you need network specialists, storage specialists, VMware specialists just to configure your infrastructure. With Ignite, a generalist can do it, and do it in minutes, so your specialists can focus on more important tasks. So you can see on this page now, everything's green and ready to go. The next step is to create a virtual data center. Virtual data centers are basically a liquid pool of resources that you can carve out from your infrastructure. Data centers can be assigned to business units. They can be assigned to customers. You can create as many as you like, and they span migration zones and geolocations. Let's create a new virtual data center for a business unit called BI, for business intelligence. We will show you a Linux example for big data apps and Windows SQL as well. Let's allocate 24 cores to this data center, 98 gig of RAM, and 4 TB of storage. It's probably good enough to run 50 or so general purpose VMs. You can enter any amount of resources to a data center. We picked 50 VMs as a good example. By the way, we support oversubscription as well, so you can oversubscribe cores and storage. It's as simple as that to slice and dice your resources. It's as easy as the public cloud. We are now ready to deploy apps, but first let's go create a virtual network, and you can see how easy that is as well. Virtual networks abstract physical networks from logical ones, removing many levels of complexity. We made it dead simple for application owners to create their own virtual networks that operate at line rates and provide application isolation. We support 3 types of VNets. Let's create a private VNet first. Private VNets are available to all virtual data centers in your infrastructure. For private VNets, you need a unique range of IPs. We also provide microservices like DHCP, NAT, load balancers. They're all built in, so you don't have to worry about additional hardware or software. It's like a self-contained SDN package, all on one screen. We also provide software-based firewalls that work at the VNet level. So if you specify a firewall at a VNet, any applications using that VNet will be protected by that firewall. So it's a great security feature, all built in. So that's it. We're all done with network, compute, and storage. We're all done on that. It's very simple. Now we're ready to deploy some apps. You can create applications from scratch using your own ISOs, or you can import them from VMDKs or VHDs. A quicker way is to use our templates, however. Our cloud marketplace allows you to download some common enterprise templates. This marketplace constantly is updated with new and exciting applications. As you can see, we support all the Windows apps, a lot of Linux-based enterprise workloads as well. Just so you know, Windows images are sys-prepped without a license. So when you need them, you have to enter a license to run them, or you can start and click through and just skip the licensing component. When you download them, they're saved to your local template store. So it comes from the public cloud down to your local store. You can also create your own custom templates from any VM instance that you want. So let's start by downloading a CentOS 7 template, and we'll also download a Windows template. As you can see here, this is your local template store where all your templates are stored. Now let's have some fun and create an application instance. So let's start there, new instance. Let's give it a name. Let's specify where to run it. We're going to pick the BI business unit. For networking, we can either choose the VNet we created or use Bridge. Let's use the VNet. So now you can see the CentOS app up and running. So now let's just console in and take a look. So just a note. So in under 12 minutes, we configured the infrastructure, configured storage, networks, compute, created a virtual data center, and deployed an app all in under 12 minutes. Pretty powerful. Now let's deploy a Windows app. Okay, let's give it a name. Let's use the same data center. Let's use the VNet we created as well. Now you can see the Windows app up and running. Let's console in and check it out. Now you can see how easy it is to deploy apps. Let's show you how easy it is to manage them. We provide fine-grained extensive stats for all the objects, including apps, migration zones, virtual data centers, hosts, and flash pools. Let's take a look at those. You can see the app view here. You can see things like vCPU memory, storage utilization. You see a lot of the activity on the workloads of CPU, write bandwidth, read bandwidths. And then we have a lot of storage statistics here around IOPS, bandwidth, also network bandwidth as well. So that's all baked in. So you have a one-point shot here where you can see everything you need to about that application. I have similar views for the other objects like data centers, migration zones. You can see those. Just a quick view there. You see migration zones as well. Now migration zones just show CPU and memory, and that's because migration zones are, as you remember, a physical abstract, not a logical one. So they're just showing the physical characteristics. So the last component here is the dashboard. That gives you a complete view of your entire infrastructure. So you can see things like migration zones, you can see the storage, you can see compute, you can see by virtual data center as well, and you can see like the hide items here. So if there's issues or anomalies or you're hitting some peak limits, this is the best place to go for that. It'll highlight those areas very easily for you. So pretty amazing. You have now seen how easy it is to deploy and use a super converged enterprise cloud. We think the benefits speak for themselves. So we offer multiple ways for you to see this product. You can get a demo from our sales specialist. We also have a virtual lab where you can log into and reserve it for a day or 2 or 3 and download your own apps and run your own infrastructure there. It's fully dedicated to you. And then third, we offer POCs where you can register for a POC and we'll ship you a 5U unit in a crate with wheels. You plug it in and go through the cool demo that you saw today. It's as simple as that. So all of this was really about drastically lowering your TCO and simplifying your infrastructure. We hope this helps, and we can take your questions now.